So I'm giving kind of a high level talk that covers a bunch of categories. Usually when I talk about secure coding, I'll get very much in the weeds. That shouldn't come as a surprise for those of you who know me at all. But for this, I try to keep it high level because I'm not assuming you're all expert C or C++ programmers. Jude did a real nice intro, so I probably don't have anything much left to say. I'm currently working as Standardization Lead at Woven Planet, which is a subsidiary of Toyota. So we develop the code for the software for Toyota vehicles, and eventually, hopefully, we'll sell software to other OEMs as well. So it's a really interesting and exciting environment, where we're developing safety critical and security critical code. So here's the agenda. Just kind of cover again at a very high level, what the problem is, and why can't Johnny write secure coding, write secure code? And that title was taken from one of those 50 or 60 papers. I think the original one was why can't Johnny read? So here's a chart from the TOB index, kind of showing the popularity of various languages. And you can see here, see if I can get my pen thing working. You can see here that, back not too long ago, I guess it's 20 years ago, we had some languages like Java and C and C++ that had sort of 20% of the market. And those things have sort of decreased in popularity. Well, now, the biggest market share is probably Python is the most popular language listed here. Now, maybe at 12 or 13% of the market. So what you've got is sort of more different languages, sort of greater balkanization, and secure coding is very much in the details of a particular language. So, if you want to reduce the number of vulnerabilities out there, solving, if you eliminate all vulnerabilities from C language programming, that would at most address 12% of the code being developed today, right? So that problem's become increasingly hard. Most vulnerabilities are caused by programming errors. This is a pretty old study, but it showed 64% were due to programming errors. A lot of times, the big question there tends to be what else causes vulnerabilities besides coding errors. But very commonly, vulnerabilities are caused by things like configuration errors, where software is sold in sort of an insecure configuration, so people who are evaluating it can get it up and running quickly, and then they take their eval software and they evolve it into their production code, but don't necessarily ever completely lock it down correctly. So a lot of vulnerabilities are just caused by insecure configurations because the way kind of the market pressures drive things. So OWASP Top 10 gives a sense of what common vulnerability classes are. I've been involved in coming up with these lists sometimes, and the way it's done is, whoever shouts the loudest gets their thing in the top 10. So it's not really scientifically done, but it's a good kind of marketing tool, and certainly a lot of people look at this. And this has evolved over the years. This is 2017 here, and 2021 here on the right. You'll see they'll introduce new categories like insecure design, software and data integrity, server-side request forgeries as new classes of vulnerability sort of become kind of emerge. And they don't really remove anything from the top 10. They just broaden the categories. So they kind of just lump things together into sort of broader category names, and so nothing really goes away. So if we look at some popular programming languages like C, C++, and Objective-C, C and C++ are still in the top 4. Objective-C has really dropped off recently because of Swift, but Objective-C is based on top of a version of the C standard. So these languages all have a lot in common. So they'll have something called undefined behaviors, which don't have to be diagnosed by a compiler, but can easily result in errors and vulnerabilities. Some people would say that undefined behavior is an error, which is not entirely true, but close approximation of the truth. So Java is a more completely specified language than C, which is an advantage from a security perspective, but can lead to inefficiencies in execution. So if the process and architecture your code is running on doesn't operate in the way Java dictates, then that behavior has to be emulated, which of course is much more expensive than just running machine instructions. And the problem with Java is it allows code from different trusted domains to run in the same virtual machine, which really creates a huge attack surface, and probably a real large class of vulnerabilities in Java deal with deserialization vulnerabilities, which basically are taking code from someone else, possibly an attacker, and executing it in your virtual machine, which how could that have ever caused problems? We'll never know. But so the way you identify an undefined behavior, if you're looking at one of the standards, is that if there's a shall or shall not requirement that's violated, that means that the behavior is undefined. So most typically, we're not trying to hide undefined behaviors in the standard. So we usually say things like signed integer overflow is undefined behavior. We just make it really clear what is and isn't an undefined behavior. And undefined behaviors are not, errors in the standard. I mean, they're given a lot of thought, and they're done this way for intentionally, and for typically good reason. And then the third, which is kind of the accident, is by the omission of any explicit definition of behavior. So this is a CYA where basically the committees just say, well, if we didn't define it, then it's undefined, and so that this is called implicit undefined behavior, while these first two categories are called explicit undefined behaviors. And usually when we identify implicit undefined behaviors, we go ahead and repair the standard to make those undefined behaviors explicit. And there's really no difference between these. They're all behaviors that are undefined. There's an annex in the C standard which has a list of these, and that's put together by the editor. It's a useful resource. Occasionally there's some mistakes in it, and so this is not this is an informative annex. The text of the standard is the normative definition. So what's interesting about undefined behaviors is that they're really there for a variety of purposes. So one is to give the compiler implementer the license not to catch certain program errors that are difficult to diagnose, right? And so, we all kind of know that there are, NP complete problems, which, such as a halting problem, for which, the diagnosis could require really an infinite amount of computing resources. So certainly this sort of leeway is necessary. In sort of the C committee and stuff, you might, for example, we might have a discussion where people like, does everyone diagnose this? And everyone does. And then Joe says, well, actually, our compiler is really bad and we can't diagnose that. And all the other vendors will say, well, don't worry about it, Joe. We'll just make it undefined behavior and you won't have to diagnose it. So they're very friendly, collegial towards each other, but that always shifts the burden to the programmer to, kind of detect these errors. And it doesn't mean that the other compilers won't diagnose it. They'll continue to do that. It becomes basically a quality of implementation issue. So the second reason is to avoid defining obscure corner cases that would favor one implementation strategy over another. One example I use is that if you take int min remainder -1 on an Intel processor, it's actually will fault, while mathematically the correct answer is 0, right? And so there are some processors that will produce a 0, but Intel's not one of them. And so the standard makes this undefined behavior because they don't want to force compilers to basically emulate the behavior of producing a 0 for this corner case, because it would tend to very much slow down code overall. And then finally, and this reason's really unlike the other reasons, it's to provide implementers the ability to provide a conforming language extension by basically augmenting the officially undefined behavior. So a good example of this is fopen. When you go to open a file, you can identify a mode that you want to open the file in. And the standard says any of the letters, if you use a different mode than the one specified by the standard, is undefined behavior. Now, doing that is not going to cause anything to crash. I mean, the reason they've done that is because file systems have really inconsistent set of functionality. And so if it's in the standard, then all file systems have to support it. So the standard only supports sort of the lowest common denominator features across file systems. So this is really a way for implementers to add additional modes to access other features of the file system, and frequently those are things like privileges and permissions and things that are really helpful when it comes to security. So when an implementation, a compiler encounters undefined behavior, it can ignore it completely with unpredictable results. In the C committee, we tend to say, the compiler is free to go off and play the game of life, because people in the C committee are really, really, really old. So we still remember the game of life. In the C++ committee, they'll talk about nasal demons and stuff, but basically, there's no guarantee at all what type of behaviors you get. It could behave in a documented manner characteristic of the environment. So again, if you say int min remainder -1 on Intel platform, it will fault, and that's a behavior characteristic of that environment, even though of course it's faulting. Or the best you can hope for is that it will terminate translation or execution with a diagnostic. So here's an example of a typing issue in C, and I use this a lot because I think, first of all, I saw it in a C++ book. so this is the sort of thing that some C++ expert published, not recognizing that the code had a vulnerability. And I'll give you a second to look at it. I really don't know if there are many C or C++ experts in the audience, but does anyone see any problem with this code? If you do, just go ahead and unmute and shout it out. So this is like a stir copy function, except it's meant to make a copy of a character array, which means that the array simply doesn't have a no termination character before the bound, right? Which is what makes it a character array and not a string. So it takes a size and it takes a pointer to the array. And we know, okay, we have a precondition that we know the size is within the bounds of the array. So no one's lying to us about the size of the array. That's guaranteed by how this function's called. So we start out by saying, okay, if they're trying to copy a 0 array, we'll just return null. That's sort of a silly thing to try. Then we'll allocate the storage we need. We'll check to see if the allocation failed. If it did, we'll return null. And then from I equals 0 to less than the bound of the array, we'll iterate and copy from the source array into the destination array. So no one's unmuted, so I'll go ahead and show you what the problem is. So the problem is that the bound here is a size t, which is an unsigned type that's large enough to represent the address space. And the iterator here is an int, which is a very common thing to do, right? Say int I is an iterator. Now the problem here is that the bound can be larger, could be larger than the maximum value that can be represented as an int. And if it is, eventually this int will, this signed int will overflow. And on most platforms, overflow is undefined behavior, but typically what it'll do is it'll wrap around and become a negative number. So if that happens, we're going to start indexing at a negative index, which of course will be outside of the bounds of the object, and we'll write outside the bounds of this array, which is, undefined behavior, buffer overflow, pick your terms. So, so very broken code, but a very common, error to make, that of course is not diagnosed by most compilers. So, why can't Johnny program securely? Programming is really difficult and often unintuitive, and compilers will frequently not diagnose common secure coding violations that lead to exploitable vulnerabilities. I showed this slide while I was prepping for this class last weekend. Someone like, oh, there's a picture of a wheat field. And that's actually exactly the point. This is not a picture of a wheat field. This is a picture of several lions, right? And so that's sort of the point of the slide is, right, it's not always that easy to see the vulnerabilities inside the code, right? They hide very, very well. So, why can't Johnny program securely? Johnny tends to be, inefficient, inexperienced, undereducated. And inefficient programmers, is a quote from Steve McConnell, they'll tend to experiment randomly until they find a combination that seems to work, right? So they'll start with some copy paste some code from Stack Overflow, paste it into their system, get it to compile, and then they'll test it until it works. And then as soon as it works for the greenfield case, right, then they'll move on. But that approach doesn't demonstrate any knowledge of the code, and it doesn't really take into account whatever sort of edge cases might exist. For example, int min remainder -1. So it'll produce code that works under these optimal tested conditions, but it by in no means is going to produce secure code. So so software development demand is continuing to to outpace supply. Here are some statistics that are pretty recent, but probably already out of date. Yeah, and so a backdrop to this is just this demand for more programmers, right? And when your demand outpaces supply, basically your quality control goes out the window, right? So you just sort of broaden what you consider to be qualified people to develop code. So according to the U.S. Bureau of Labor Statistics, the demand is expected to grow 22% during this decade. About a little under 200,000 openings for software developers each year over the decade. Some of this is going to come from people, I want to say people like us, certainly people like me who are thinking really hard about retiring one of these days pretty soon. Yeah. And the supply, the U.S. produces about 65,000 students a year, which you can see as, well short, maybe a third of the demand for new programmers. So increased capacity can be addressed in part by increasing the productivity and efficiency of people learning computer science. Basically being able to move more people more rapidly through course materials. But that's kind of matched by need for quality, right? So if you're poorly educating students, that's not going to improve the situation. You just have more people writing more bad code, which doesn't necessarily take us in the right direction. So effective secure coding requires, really a balance of things. So you have to understand high-level theory. You really need to develop the detailed engineering expertise, and you need to apply both of these in the context of developing secure software. So it's very challenging. I think a lot of developers probably stop developing and move into management or related fields before they really even get to this level of proficiency. So the further problem is how we assess developers, and I mostly wrote these slides because at the time I had a testing and evaluation, a testing company where we were trying to test the performance of developers. But it's true nonetheless. I mean, objective assessments such as multiple choice is a cost-effective way to assess developers, but it doesn't really demonstrate their ability to write software, right? So, for example, you probably wouldn't feel comfortable getting into an airplane that was being flown by a person who passed a multiple choice exam about how to fly an airplane, right? You kind of want to know that they've demonstrated their ability to actually fly the plane before you put your life in their hands. So the same kind of makes sense for programmers. You want to basically assess their ability to actually write code, not just to answer multiple choice questions about code. So short answer questions, provide some degree of performance-based assessment, but it has to almost always be a minimal type of task, and so it can't really evaluate the ability to do anything substantial. And the short answers are typically graded manually. I mean, often by grad students, and so that leads to sort of inconsistency in assessments, and also pretty high costs in order to do the developer assessments. So something that I'd been working on a few years ago, and it's now it came out of CMU, but it's now defunct, is this authentic assessment that measures the test taker's ability to program realistic problems. So we have basically a testing environment where they write some code, and then the code is then assessed using a bunch of sort of automated testing. So you get a repeatable assessment because it's done by the tools. So why can't Johnny program securely? Because basically his education was lacking, and the assessment of his abilities was inaccurate. So Johnny basically got hosed over pretty bad. And I'll tell a quick story about CMU. I taught secure coding at CMU for 14 or 15 years, and one of the first things I would have to do is tell them all the stuff that their previous classes had told them that was just wrong, and I'm not there anymore, so no one's telling them anymore. So even CMU students who are among the best in the world, they're being lied to and given bad information and then sent out in the world. So so education is problematic. So I really didn't want to get into kind of men and women, and but I really want to call this talk "Why Can't Johnny Code Securely?" just because of the "Why Can't Johnny Read" thing in the 50s. And so because of that, I had to sort of address why can't Susie program as well, just to make it clear that I'm not just this talk isn't just about men, this talk is about programmers. But women's share in computing has declined to 25% in 2020 after reaching a high of 34% in 1990. And so typically, the reason for women entering, not entering, or not staying in the field has a lot to do with, the environment, kind of the tech bro culture and, their perception of the field doesn't have anything to do with their ability. I mean, I think in general, women are a lot smarter than us, and we let us live based on their tolerances. Okay, so that's education assessment. So next is sort of tooling and processes and techniques for producing secure code. So the percentage of bugs that are eliminated by software reviews, inspections, and tests. If you have a total of 100 defect reports and you remove 90 of them, you'd have a defect removal efficiency of 90%. So formal inspections, Fagan inspections that IBM invented, I want to say back in the 60s, has been measured to top 85% in defect removal efficiency with more than 40 years of empirical data. Inspections also raise testing defect removal efficiency by more than 5% for each test stage. Static analysis analyzes software without executing the software. So most analyses that can be done statically would produce useful results or tend to be NP complete problems. The time required to solve the problem using any known algorithm increases very quickly as the size of the problem grows. And so the time required to solve even moderately sized versions of many problems can reach into billions or trillions of years using any amount of computing power available today. So these problems are often addressed by heuristic methods and approximation algorithms. Static race detection tools provide an approximate identification. So this means that algorithms are prone to false negatives where vulnerabilities or defects are not identified, and false positives where incorrectly, normal working code is incorrectly identified as a vulnerability or a defect. And so you can kind of tune your tool to produce either more false negatives or more false positives, but very hard to write useful, sound, and complete analysis. So static analysis has a high defect removal efficiency, frequently topping 65%. So exhaustive testing with all possible combination of inputs is not viable. Most forms of testing are below 35% in defect removal efficiency, or remove only about 1 out of 3 bugs. All tests together seldom top 85% in defect removal efficiency, and 7% of bug repairs introduce new bugs, right? Which is always an issue when you think about performing maintenance on code, right? That many changes are gonna introduce defects. So software testing can typically demonstrate the presence of bugs, but it's very not particularly good at demonstrating the absence of defects. So as we find in fixed problems, we can raise our confidence that the software performs as it should. And so testing is important, but it doesn't ever guarantee that all bugs have been removed. So testing is not a panacea. And here's a picture of early Earth, and I think this was called the Panacea continent. Don't correct me if I'm wrong. And so it won't eliminate all the defects and vulnerabilities injected by our undereducated and inexperienced Johnny, who kind of got out of school without really learning, how to program correctly, or having his skills properly assessed. So dynamic analysis tools integrate detection with program execution, so the actual runtime environment is tested and not simply simulated. So analyzing the actual execution flow produces fewer false positives because if it'll only detect actual problems that occur. But the main disadvantage of that is that it's not going to consider execution paths that haven't been taken. And so you have to have really good code coverage in order to ensure that you're going to detect potential vulnerabilities. And there is also significant runtime overhead associated with dynamic detection. So typically this is just done during test time. It's not something that you can enable or that's typically enabled when you deploy the system to production. Okay, so what can we do better? And this is a really short section. I think it just has this one slide. So, and I had some more slides, but I didn't think they were applicable to this audience necessarily. But so anyway, my one suggestion here that's a little bit focused on education is this topic called security injection. And I did some work with Towson University in Maryland maybe 10 years ago to work on security injections. And the idea here was, if you're teaching a secure coding class, you're doing it wrong, right? You shouldn't ever teach a secure coding class. You should just start out by teaching students how to write correctly, right? Don't teach them how to write poorly, write bad code, and then hope someone will come along later and fix, have them unlearn what you taught them and teach them the right way, right? So, and it's very hard to use this approach because it's very hard. We made this point earlier. It's very hard to write correct code, and universities like Towson, they have to keep students interested in in the material and in staying enrolled in the program, right? They don't want to scare people away. So it's a careful balance. And here I just posted this. I wrote this book, Effective C, and originally it was supposed to be a crash course. It says an introduction to professional C programming, and people have a hard time categorizing this book because it is an introductory text, but it doesn't water anything down. It's very it goes in and explains how you code correctly in a very detailed and correct way. And so there was this reviewer in the UK who basically writes, too much detail, man. Excruciating. Move on already, right? So this guy here. This is the problem, right? This is what we have to deal with, is people who don't have the patience to learn how to write code correctly. But because because we can't find programmers, we're probably going to hire him anyway, and he's just going to muck things up for us. So that's it. Problem is Johnny's not properly educated. Secure coding is really extremely difficult. Testing and analysis, even when performed in a state-of-the-art manner, is not a panacea. And no one really does it in a state-of-the-art manner. Maybe NASA is giving it a go once or twice. It's better to produce fewer but better trained software engineers. That's my opinion. I said that once on Twitter and I got flamed for saying it. And to improve software security, we really do need to attack this at every level, increase in better analysis, improve testing, and better trained and better educated programmers.